So let's get started. So welcome join us. The proposal title is Enhancing Modern Threat Intelligence, the pivotal role of large language models in extracting actionable TTP attack chains. So I am Laurie. And Tara.
And Tara.
Yeah, we are from 360 奇虎 company, 奇虎360, 谢谢. So this is the agenda for the presentation. The first part is background. In the background part, we will introduce the TTP concept, the significance, and the challenge of TTP injection and the conversion, actionable conversion from human-readable threat intelligence. The second part, solution introduction. We will introduce the proposed solution. We are focusing on key modules and overall architecture. In solution implementation results, we will firstly introduce the evolution of TTP injection and highlights the KGRAG-based TTP injection, which gets the SOTA results. We will then introduce the whole KGRAG to enrich extracted TTP chain by adding more TTPs which may have been missed or ignored in the original threat reports. At the end of the part, we will introduce how to use LLM with RAG to convert an extracted complete chain into actionable ones. Finally, we will provide the takeaway. Having reviewed the agenda, let's begin with the first part. Understanding TTP is quite critical for threat hunting and defense, and they revolve at adversaries' objectives, methods, and implementation details. Fortunately, cyberattack provides a unified language for TTP exchanging and use. So let's start by understanding TTP. The tactic, the stage-specific objective of an adversary attack actions. The typical examples are initial access, privilege escalation, and lateral movement. The methods adversary use to achieve their tactical goals. For the tactical example are precise injection, pass the ticket, golden ticket, some kind of technicals. The procedure, the specific implements the adversary take to execute a technical. For example, APT29 has used the Mimikatz to exploit domain controller via zero-login vulnerability. Now that we have outlined the main concepts of TTP, let's discuss how they play a critical role in upgrading our defense strategies. We already know that most SOCs have begun to shift from passive defense, IOC-based detection to proactive defense. However, most useful TTPs are reflected into threat analysis reports. So, as human-readable format. So this is a reason why we needed to extract them out. Also, most extended DR and same kind of solution can correlate TTP sequence to generate detections or alarms. Another factor is that the meta attack has provided a model, detection modeling consists of data source, data components, and the detection suggestions. For example, precise injection, we should pay attention to the file meta change in the data source file, name the file, and pay attention to the system calls in data source process to generate a correlated result. So accurately, along with threat detection modeling based on TTP granularity, this is the reason why accurate TTP injection matters. So let's continue to talking about why the significance of TTP actionable conversion. Through conversion, TTP intelligence can be converted into actionable, more practical ones. It enables real-time detection of code-level attack and rapidly respond by SOA in SIM or extended DR, such kind of solutions. It also can bring actionable TTP into simulatable and executable attack scenarios. For example, you can put them into a reader, blue reader drills, penetration test, and bus platforms to provide variable improvement measures for defense system. The red picture shows practical TTPs used in our company's product. So there are also multiple challenges of TTP extraction and actionable conversion. Let's first look at the challenges of TTP extraction. One major challenge is that most reports are designed for human-readable format. There's no any structured TTP data. And the reports also contains abstract results, abstract contents. For example, the analyst will only focus on novel or critical behaviors in the campaign. And the reports also contains other subjective descriptions. For example, the analyst may ignore or miss the assert or execution environment information purposely. Let's continue. Let's move on to the challenge of TTP actionable conversion. As we know that currently the work is done all done by manually, which is extremely time-consuming, and it also depends on personnel domain knowledge and skills. So let's take a closer look at how our proposed solution to address them. There are 4 core modules in our solution pipeline. First, attack path generator. Attack path generator used to analyze reports to extract attack path descriptions. Second, TTP chain generator, which used to convert unstructured attack path descriptions into structured TTP chains with standardized data. Third, TTP chain enricher, which used to supplement TTPs in the chain to ensure both completeness and reliance on the attack chain. First, actionable TTP chain generator, which used to translate the structured TTP into executable code and automation scripts for the future defense tasks. Let's look at the whole picture. This is a solution architecture diagram. The pipeline, the input of the pipeline is various reports, thread reports such as APT, ransomware, miner, such kind of reports. And it also supports internet URLs, supports PDF, Word, plain text, such kind of Office document format. The output of the pipeline is social phishing corpus, Lua generation scripts, and Metasploit framework-based module execution commands. In addition, the pipeline used the knowledge graph to store the data with designed relationships. The schema is a bit similar to CTX format. In the presentation, we will focus on TTP extraction and the actionable conversion by TTP chain generator, enricher, and the actionable TTP chain generator. We will introduce them one by one in detail later. So now we have outlined the challenge of the proposal. Let's take a moment to introduce how we address them. Before introduce the KGRAG-based TTP extraction, we will introduce the evolution of 3 of the TTP extraction from traditional AI technology to cutting-edge generative AI solution. So Port will introduce the part.
The TTP extract process using traditional machine learning typically involves several steps, from data pre-processing to model training and prediction. INN or STM can also be used for TTP extraction. INN has memory capability and is good at processing long sequence, whereas TMs address the issue of forgetting. Here are several representative works use traditional machine learning or deep learning method to extract TTPs. There were several limitations using traditional machine learning or deep learning method to extract TTPs, including excessive pre-processing, feature engineering dependency, and the weak generalizations. Well, Bird had taken TTP extraction to the civil age as it enables deep understanding of text. Fine-tuning pre-trained models for TTP extraction typically involve several steps from preparing high-quality training dataset to model deployment. Here are some representative works use fine-tuned pre-trained models to extract TTPs. Well, there are two limitations using fine-tuned pre-trained model to extract TTPs, include the lack of domain knowledge and the bias training dependency. Well, generative LLMs take TTP extraction to the next level. They have two main outstanding advantages. The first advantage is that generative LLMs have vast knowledge of human language, code, and the technical concept. This allows them to parse and contextualize complex attack behaviors. The second advantage is that generative LLMs offer natural interaction and adaptive output. Using prompt engineering, they can generate structured TTP information. For example, in the red picture, the DeepSec R1 was asked to extract TTPs from a threat report, which described how a threat actor deploy a backdoor and collect data. The end output, the JSON format TTPs, that looks good. But it is sufficient using ML alone? The answer is no. There are two main issues using MM to extract TTPs. The first issue is the outdated training data. MM typically trained on data up to a certain point, but the TTPs and man attacks are continuously updated. How can they identify these new techniques? The second issue is hallucination. LLMs may generate fictional or irrelevant TTPs. Let's examine the earlier example more closely. Check the first TTP. The extract procedure is that the threat actor abused the section env service to load a malicious DL. When the legitimate service started, it loaded the malicious DL. Right? It's hijacking action flow. The technique is correct, but the tactic is wrong. Hijacking action flow belongs to tactic defense evasion, not initial exercise. We also found that the MM needs a TTP about mutual exclusion. The TTP is missed due to the M didn't know the new technique released in October last year. We use RAG to address about issues of M's for TTP extraction. First, RAG integrate continuous updated domain knowledge to help M to identify new techniques. Second, RAG provide accurate context information to reduce hallucinations. Next, let's introduce the implement of KGRAG-based TTP extraction approach. Our KGRAG-based TTP extraction process mainly consists of two tasks. The first task is generating baseline candidate using fine-tuned pre-trained model. The second task is retrieving similar TTPs and using LLM for TTP extraction and rethinking. Specifically, our fine-tuned pre-trained model provides the following improvement. The first improvement is that distinguish primary and secondary techniques to improve the differentiation between procedure. The second improvement is that you extract TTPs from diverse artifacts, such as tools, command line, for more comprehensive coverage. The bottom right diagram, The bottom red diagram is the process of the second task. The input mainly includes two parts. The first part is the candidate TTPs from the fine-tuned pre-trained model. The second part is similar TTPs with related metadata retrieved from the vector store. Then, we prompt M to extract TTPs and output in structured JSON format, with candidate and similar TTPs as reference. After that, the rethinking module will provide additional context, such as detailed definition of techniques, correct example to help the MM to assess the extract TTPs and remove the irrelevant or incorrect ones. The table shows the performance of different approaches for TTP extraction in different ages. We can observe that our KGRAG approach gets the best performance. Next, Lauren will continue to introduce the remaining key modules in our solution.
Let's continue to look at another key module in the solution implementation, KGRAG-based TTP enrichment. So recalling what we mentioned earlier, there are multiple challenges in the TTP extraction task, among which the three reports also focus on novel or critical behaviors. And the three reports also ignore assert and execution environment information purposely. For the TTP chain, enrich module its workflow consists of three tasks. The first task is use report metadata to get possible TTPs. Specifically, the LLM will analyze current report to get the meta info such as adversary information, attack parity, and attack vector and regions. Then use such kind of metadata to retrieve same TTPs from same adversary or targeted by same vector or regions. The module also can list the popular TTPs at the same time. Then use the LLM identity caps in the current TTP chain. We have designed many built-in props. For example, is there a description of initial access in the reports? Or if there are any descriptions on how adversary gains a higher permission, then use above context to reason the most appropriate TTPs according to the situation of the previous or next TTP in the chain. In summary, the reasoner engine will reason TTPs from the perspective like permission change and assert change. We have tried three solutions showing the slide, and the last one got the best results. The core of this solution is the use of lightweight domain language and custom AI tools, which based on Apache Jena reasoning engine. It has achieved remarkable results in completing tasks. Okay, let's continue to look at the last key module in the solution implementation, actionable TTP chain generator. So the input of the module is the compilation structure TTP chain. The output of the module is the social fiction text, layer generation scripts, and the meta-slave framework module execution commands. There have been many studies in the industry to use LLM to generate social phishing corpus. So we will quickly pass here. Then when generating lure generation scripts, this is important to use LLM with code mode to generate code. This way, which can ensure the code accurate and executable. The third case is the test of skill. We all know that there are a lot of penetration platforms. Choosing an open source one which with rich documents is most important. In the solution, we choose the Metasploit framework, and it has rich documents. In third case, we developed a set of processes that simulate interaction between humans and the Metasploit console. That is, program search possible modules through LLM provide keywords, and later LLM select most appropriate modules based on rank scores and descriptions of the searched modules. Then LLM finally reads the module documents to generate running commands. If no suitable module is found or the found module doesn't meet the requirements, LLM will generate a new module and finally load and execute it. Judging from the test results, all three kind of generations have achieved good results. We will take a closer look at this process through pipelines, input and output key logs. This is the first sample. The first sample is social phishing text generation. On the left top is you can see the original report phishing related chunk is presented in the human-readable format. And the left bottom is the TTP instruction result. The TTP result contains the description, technicals used, and specified artifacts, and about original mail information. And finally, it has been covered into multiple phishing corpora that fit the TTP. This is a second sample on a lure generation script. Similarly, after the original report chunk is extracted into structured TTP, a lure generation script will be generated based on the TTP details. After the script is executed, a lure that meets the TTP will be generated successfully. The third sample is on Metasploit framework module use. The left top shows the original human-readable report chunks. After KGRAG-based extract, the TTP contains description, artifacts about the CVE, target asserts. It is worth mentioning that it contains permission change information, which will possibly be used for reasoning about the TTP chain compilation. The red top shows the prompt engineering that LLM provides the keywords to search possible existing modules. And the right bottom shows the prompt engineering let LLM choose the most appropriate module. And due to possible module update and possible hallucinations, we fit the module information to let the LLM generate final accurate commands. The first sample shows how to generate a new Metasploit module if there is no existing module to use. We can see the result. When the LLM provides keywords, we use the keywords to search the Metasploit console. There's nothing module found. So we pass such kind of information to LLM, use the LLM to generate the new module according to the Metasploit framework APIs. Finally, this module will be loaded and executed. So to summarize, our presentation today has highlighted several key innovations and methodologies. It converts human-readable reports into actionable TTP attack chains. So we provide such 4 takeaways. It provides a practical pipeline to automatically convert human-readable threat reports into actionable TTP attack chains to support the practical application of TTP intelligence. Then propose a paradigm that combines lightweight BERT model predictions with KGRAG to ensure high-precision TTP instruction using up-to-date data and avoiding hallucinations. Third, propose a method that leverages KG reasoning to systematically enrich TTP attack chains by linking possible TTPs. Finally, propose a method based on the RAG that converts structured TTP into actionable intelligence in diverse formats. So that's all. Thank you for all your your attention today. We hope the solution will provide you valuable insights and inspire new approach for the industry. So do you have questions?
If there are any questions, we can have more. There are 2 microphones here.
Hi, good afternoon. I have a question. How do we ensure that LLMs or LLM do not introduce bias or misinformation when analyzing cyber threats? Thank you.
Actually, this is a enrichable module. So we just the first task is to instruct the already existing TTPs in the original 3 reports. But we found the reports will only focus on critical or novel TTPs, novel behaviors. For example, we may find that there is a TTP about privilege escalation, but there is nothing to describe them. So we need to find the TTP to link the next TTP. Yeah.
Hey, thanks for the great talk. I know KGRAG is primarily used for like diseases, like that's what it was primed for originally. Did you have to modify KGRAG in any way, like maybe I missed it, in order to work well for TTPs? I know you went through like fine tuning and BERT and everything, but I'm just curious if you're finding that KGRAG can manage any kind of knowledge graph, or if you had to play with it for it to work well with TTPs.
Actually, the question you mentioned about the KG knowledge graph, why we use the KG, right? Actually, when we use the KGRAG, the KG is a critical part in the solution because the knowledge graph contains the relationships and the entities information. For example, our task is to generate TTPs. The TTP consists of tactic, technical, and procedure, and other artifacts such as CVE, target asserts, use the tool, and other critical information. So we store this kind of information with their relationships into knowledge graph. Then we extract them out because we use the RAG method, we need to add more information, useful information to feed the promoting engineering. So the relationship is very useful because the result, the output of the extraction task is also the relationship TTP related. So this is the reason why we choose the knowledge graph. Yeah.
Thank you.
One more question here.
Okay.
Hi, my question is about the choice of BERT as LLM in this case. So why did you choose BERT specifically? Because it's quite lightweight, as you say. Have you tested other LLMs to have a comparison? And then when it comes to the fine-tuning of BERT, how did you fine-tune it? I mean, what kind of data did you feed it to get it to be well-performing?
Actually, we don't use BERT. We just use the BERT variant. Actually, there is so many variants about based on BERT. We actually, there is fine-tune works. So we just need to prepare the training data, then choose the good model, such as BERT, Robert, and other Chinese pre-trained model. So we just choose the best, which one has the best result. So the training data actually is very important. Let's recall this slide. Sure. We just, for example, there are so many technicals in the MetaTech, about 700, more than 700. But we cannot put them all in the training data. We should focus on the critical technicals, because there are some technicals are just a tool used or schema used. So we just focus on the main technicals. So this is a first important reason. And then we also need to manually operation to get the accurate TTP based on the context of the reports. So this is two critical parts when we training the BERT, training BERT variant small model. Yeah.
Thank you.
Right. I think we've only got one question. Well, we are close. So, I think the speakers are here, so you can walk over and talk to the speaker afterwards. And let's thank again the speakers.